Hello.
Good morning, sir.
Good morning. Good morning. Just wanted to check my audio and
Yes, sir.
cameras are working.
Audible, sir.
Okay. Okay. Should I check once quickly whether I can share my screen?
Sir.
Just give me a second. Okay, so let me share my screen and let me know if this is visible. So okay, so if I share, your sharing is going to get disconnected. Okay, just for a while. Is that okay? Hello, am I audible?
Yes, sir.
Yeah, so I wanted to check my sharing once. Can you confirm if you can see my sharing?
Sure, sir.
Can you please confirm if it is visible?
Yes, sir.
Okay. Okay, so I will stop sharing now. So I will drop off now. I will join back at 10 a.m. Okay.
Okay, sir.
Okay. Thank you.
Good morning, Avik. Good morning, Avik. আমি কথা বলতে পারছি না কেন?
না ও বেরিয়ে গেছে, 10টার সময় লগ ইন করবে আবার।
না সে ঠিক আছে, কিন্তু আমি এখানে কথা বলতে চাই। আমার কথা শোনা যাচ্ছে এখানে?
হ্যাঁ, ও বেরিয়ে গেছে তার জন্য।
না আমি জানতে চাই যে আমাকে এখানে মানে তোমার পুরো মানে শোনা যাচ্ছে, দেখা যাচ্ছে?
হ্যাঁ, কথা বলো না, এটা অলরেডি লাইভ আছে এখন। হ্যাঁ।
ওকে, ঠিক আছে। ওকে। Good morning, Avik.
Good morning.
So all good?
All good. My
Uh,
I hope my voice quality and video is good.
yeah, absolutely. And thanks for accepting our request
No
and
problem. My
coming
pleasure.
here to live session. Now, the today's session would be like we. From here on, my colleague Mr. Ketan Mangala will take over from this session here. He will be the session moderator. He
Okay.
will be giving a brief overview on the conference and subsequently will be introducing you to the audience, and then you can share your contents and then can take this over, and at the end you can take selected questions from this session which will be handled by Mr. Ketan Mangala. Is that fine?
Yes, absolutely.
Is our audio okay from here?
Audio, right now it's okay, but when you were speaking, I think there was a little bit of echo coming, but right now it looks okay.
Yeah. So are you could you understand that what would be the session?
Yeah.
Okay. So we are just 2 minutes away. It's 58 right now. Maybe in 1 minute, I'll hand this over to Mr. Ketan Mangala, who will take this session ahead. Okay.
Okay.
So thanks again, Avik, for for your concern, for your time from your busy schedule. Thanks again, and we'll be connecting separately once the session is done. Yeah.
Sure, sure. No problem. And it's my pleasure. Don't worry.
Hello, and good morning, everyone, and welcome to the final day of ICAP 2021. We have had a wonderful event for the past 2 days with scholars and academicians from around the world presenting their research and a distinguished speaker series. And to cap off the same, today we have Mr. Avik Bhattacharya to talk on the changing requirements from 4G to 5G with respect to the time criticality of the RAN transport. To introduce you to him, Mr. Avik Bhattacharya is a senior product manager in Keysight for the layer 2-3 network infrastructure test solution. Mr. Avik Bhattacharya has more than 13 years of experience of working on the cutting edge technologies. He is focused on validating the next generation networks that enable connected world of the future. He has worked with the networking needs of telecom, automotive, industrial, and cloud data centers. Avik holds several patents to his name on validation methodologies and is a frequent presenter in technical forums and industry events. We at ICAP 2021 are honored to have Mr. Avik Bhattacharya as an invited speaker today. May I now request Mr. Avik Bhattacharya to take over the session. Sir.
Thank you for your very kind introduction, and hello to everybody. Good morning, good afternoon, and evening to people who are joining from other parts of the world, maybe. And it's a pleasure, being part of this conference and being able to present some of my experiences from the networking industry. So I will share my screen, and can somebody please confirm if this is visible? Is it visible?
Uh, yes, sir, it is.
Okay, so today's topic is going to be the time criticality in the 5G RAN transport networks, or the radio access network transport. And uh, the reason we want to talk about this topic is, this is some of the things which is right now changing the world, right? So in today's world, if you look at the network designs, they are driven by the application needs, right? What the application needs. It's not because somebody suddenly doesn't like 4G and that's why 5G is coming into play. The reason 5G is coming into play is because that's what the application needs. We want to play video games in virtual reality, and to be able to support those kind of applications, we need an overhauling of the network, which is what kind of 5G is. So as the era of 5G ushers in, the demand for the new services like the bandwidth hungry video, or the IoT, or the industrial IoT, the industrial Internet of Things, or even low latency connected cars. These these kind of things are expected to see massive increase, right? And to classify these applications better, classify these applications better in terms of 5G with respect to their application need, 5G community has put forward set of terminologies. And these terminologies are nothing but, as you can see on the screen, they're nothing but categories of different type of application based on their needs. So first of all, we have the EMBB, or the enhanced mobile broadband applications, which are specifically the high speed use cases. We have the applications which are typically used for industrial and Internet of Things kind of applications, which requires massive machine type communication. So they are known as the MMTC. And then finally, we have the ultra reliable low latency communication, which are again specifically used for industrial automation, also known as the URLLC. Now, key to making these like services work, it depends on how you design the network, and each of these categories will require a different type of network design, right? So it's the design capable platforms to supply the high-end computing and ultra low latencies that are required here. So the clouds that support this are becoming more and more distributed in nature, offering superior performance and throughput. The edge cloud and the cloud radio access network platforms will be vital here to support this advanced and immersive technologies examples that I took here. There are options here for combining the edge cloud with the cloud radio access network as well to provide this extremely low latency use cases, and even improve the operational efficiency. So before we jump into that, let's quickly try to look at the fundamentals of how a 4G network looks like today, or I should actually say in the past. It's almost everywhere in the world 5G is coming up. So uh, let's understand the fundamental difference here. So if you look at the slide here, in case of 4G, the antenna sits on top of the tower, which transmits the radio signal, which is again used by, if you can see the green line, where the user equipment latches onto that radio signal and thereby transmits data. But on the back side of the antenna, the radio signal comes from the left hand side, which is the core of the network. That's where all the data centers and all the data sources are situated. And when the data comes towards the tower, it comes over an IP network, IP Ethernet network. It's the job of this base station unit that you can see as a black box at the bottom of the tower, that it's its job to translate that IP or Ethernet based data into radio data. And that data then gets transmitted over a pair of fibers towards the top of the tower in the antenna, and then the antenna transmits the radio signals. So this is a dedicated fiber that used to connect the antenna with the base station unit in this type of an architecture. But as you know, the need for more and more reachability became prominent. So we needed to have more and more radio units or the antennas towards the where the application users are actually situated. And then it's difficult to install the base stations in each and every remote location. So therefore came the need for a distributed architecture where the base station unit can actually be sitting separately remotely from the antenna. So one base station unit can cater to multiple antennas and therefore bring in scalability. So we will discuss a little bit in details about this, but let's move on. By the way, the picture that I've used here, I kind of used it from internet. I didn't make it myself. This was a very good representation, and I thought this will help us explaining the fundamentals of 4G network architecture. So moving to the distributed network architecture. So this is a picture that shows how the different components of the radio access network are situated in a classical model. The radio unit, the distributed unit, and the CU, they are situated in the same place. They are co-located, right? So the operators are interested in moving to a flexible RAN architecture, which basically enables them to address the different application requirements by locating the storage, the compute resources, and at the either they can be located at the base of the cell site, or they can decide to locate it in a centralized hub away from the cell site. For example, the operator can support a latency sensitive application using something called a multi-access edge computing data center that is located closer to the cell site. So here are three terminologies that probably we are going to use throughout the presentation: the RU, DU, and CU, and it's important to explain what these are. So the RU is the radio unit that handles the digital front end, and they are the parts of the physical layers and as well as the digital beamforming functionality. So the key considerations of RU design is like weight and power consumption, and that's very important. So the RU cannot consume a lot of power because it sits in a remote location. It will be difficult to provide all those power to them. The DU, on the other hand, is called the distributed unit, and that can sit close to the RU and runs the other functionalities like the RLC or the MAC or some part of the physical layer. And the CU is the centralized unit that runs the other layers of the radio data. That's it's called the RPC and the PDCP kind of layers. So the point here is, in a classical model, the BBU functionality, right, that's split into the two functions as the distributed unit, which is responsible for the real-time layer 1 and layer 2 scheduling functions, and the centralized unit, which is responsible for the non-real-time and a little higher layer like the layer 2 and layer 3 function. So the centralized baseband deployment allows the load balancing between the different RUs, and that is why in most of the cases, right, the DU will be co-located with the RU, and it could be on site, sitting on site, conducting all the intense all the intense processing tasks, such as the first Fourier transform or inverse first Fourier transform, whatever is required there. Now we are not getting into details of how the radio transmission works here, but the point here is the edge-centric baseband processing delivers low latency and seamless mobility with real-time interferences and optimal resource of usage, etc. But the other approach where is is to separate the DU from the RU. And the reason it is important is, first of all, to reduce cost. If the DU functionality is not present at the edge, then we can produce less intelligent RUs, which of course will be less expensive. And then the second reason is sometimes ability to look at a sector of RUs at once and not just as an individual RU. So this will help enable features like coordinated multi-point or higher performance transmission. And finally, as the processing gets done at the DU, the resources, right, the computing resources can be pulled in a data center where the DU resides. It doesn't need to be at the tower location. So that's a huge advantage. So that is the reason people talking about this type of architecture where the DU is separated. But what it really means is the connection between the DU and the RU will no longer be a dedicated fiber, like I showed in the first slide, where in case of a design where the DU sits at the bottom of the tower, they can be connected with the RU with a dedicated fiber. But in this case, it's remote, and the only option to connect the DU with the RU is to use some kind of an Ethernet-based network. So this, and we will use this terminology more in this presentation, but this Ethernet network is what is called the front haul. And from a capability perspective, this front haul needs to transport the this front haul needs to transport the radio data or the IQ samples that are generated in the DU over the Ethernet network so that the RU can use it. So that is the underpinning of today's presentation. In order to carry this RQ samples over an Ethernet-based network, the network needs to support certain characteristics from the time criticality perspective. It can no longer be just like an best effort Ethernet network, because the radio signals are time critical, and if they do not reach the radio unit on a time, there could be problems with the transmissions and how the mechanisms work with beamforming for the UE site. And again, we don't want to get into that details, but the point that we want to take away from this slide is the front haul network needs to support time critical traffic. Now, there are different approaches for designing this cloud RAN. That's why we call it the flexible cloud RAN. So the DU server and the relevant software could be hosted on a site itself, or can be hosted in a edge cloud, like we said, which is a data center or a central office. And that depends on the transport availability and how the front haul interfaces are designed. The CU's server and the relevant software can be co-located with the DU, or it can be hosted in a regional cloud data center separate from the DU, right? And the actual split, the decision about the actual split between DU and RU may be very different depending upon the specific use cases. Now, the other thing, so what you see on the slide is 4 different design consideration how DU, CU, and RU can be placed in the network, the radio access network. But what we need to keep in mind is that we have a huge deployment of 4G networks today from the operators, and operators are not just going to throw away the 4G deployment and suddenly bring in a new architecture for 5G network. So for quite a good amount of time, the 4G architecture and the 5G architecture is going to coexist. So these are called standalone and non-standalone deployment. Standalone deployment is where a 5G is built from scratch, and non-standalone is where 4G and 5G networks will be coexisting. So these are the design consideration. Again, one needs to keep in mind what it really means is if we really have a Ethernet network like front haul, that should be able to carry the radio data as it was used for 4G, which is also called CPRI or CPRI, and the radio data that is going to be used for 5G, which is called the eCPRI or Ethernet-based CPRI. So it needs to support both. That's another complexity that is present for this front haul network. Now, as we understood by now, probably that latency is a very important characteristics of this front haul network, and I explained why. But let's take a look at it from the packet structure and encapsulation perspective. How the functionalities are split between the RDU and the RU. So here in this picture, what you see is at the top of the stack in the slide, we have the IP packet. And at the bottom of the stack, we have the antenna. So it's like the traffic flowing from top to the bottom, core towards the antenna to the radio side. So as we move down the stack from IP to RF, we also have the lower latency tolerance because it's radio data. For example, an IP packet is not really latency bound, but a radio clocking signal needs to be within a very low latency limit. So as per the 3GPP standard, the 5G, for the 5G, the network is designed with a higher layer split and a lower layer split. Again, these are terminologies in 3GPP used, which basically defines where the DU is going to be placed. I've showed in the previous slide that DU can be placed in different parts of that RAN, but at the terminology that defines it, it's the higher layer split and the lower layer split. Now, it's the split that one operator is going to use that's going to define which part of the RAN needs to carry real-time data and which part of the RAN can live with non-real-time data. So because of the lower layer split, the DU sends and receives the IQ samples and to and from the RU in EC pre-encapsulation frames, like I said, and these IQ samples are time critical in nature and consumes bandwidth much more than the actual user data rate. So naturally, the front-haul transport network must be designed in a way so that it minimizes the loss and delay while carrying the high bandwidth traffic. To solve these problems, there are different IEEE working groups that are working on this. So like I said, the Ethernet is by design not it's not designed to support low latency, or rather I shouldn't use the term low latency. The deterministic latency application, deterministic latency traffic. So IEEE working groups are working on technology called TSN, or time sensitive networking, that makes Ethernet that gives Ethernet the power to provide deterministic latency. And we will get into detail of what TSN is. Now, 802.1cm is a profile, again defined by IEEE, to be used for the 5G RAN transport. And in the front haul network, these, what you see on the slide, these are the permissible latency values that is standardized by the 802.1cm for the front haul network. And between the RU and the DU, the one-way latency is 100 microseconds, which means that if a fiber, if fiber introduces by the laws of physics 5 microseconds per kilometer, that gives a budget of 20 kilometer of length of fiber. And sometimes the need, which is basically a limitation that puts on how far the DU can be from the RU. So we also need to consider, I mean, it's not only the fiber delay, right? We also need to consider the delay introduced by the switching elements that are going to be sitting in the in the front haul. If you look at the mid haul, it's a bit relaxed compared to the front haul. Again, it's because which part of the network needs to carry the real-time critical traffic. So that's on the latency part. And then we have the frame loss, and frame loss allowance for different class of services are different. While the user plane and the control plane data, they can tolerate up to 1 frame loss in every 10 million frames. The tolerance for in-plane data or the management plane data is up to 1 frame loss for 1 million frames. So latency is bounded, like I said, and which might be very stringent for something like the URLLC, or the ultra reliable low latency cases. And required front haul bandwidth depends on the total channel bandwidth, the MIMO layers that are being used, and a lot of other factors like number of sectors. And so it could normally be ranging from 10 gig to 25 gig or even 100 gig for some use cases. So to solve this problem, like I said earlier as well in my previous slide, 802.1cm defines, and it makes a suggestion of using frame preemption as a mechanism. Okay, so frame preemption is basically one TSN technique, TSN is a group of techniques that are standardized by IEEE to make Ethernet time critical, and frame preemption is one of those techniques that provides, that is able to provide very, very low latency in a non-engineered network, right? So at this point, let's deviate a little bit from this RAN topic, and let's try to understand how TSN and frame preemption works. And we will come back to RAN because it's important to understand the working philosophy of frame preemption a little bit. So TSN as a standard, like I said, it's a group of standards. It works in the data link layer, and its philosophy is to make Ethernet time critical by using different mechanisms. So in its toolbox, it has different mechanism like bandwidth reservation, as you can see in the slide. It offers different traffic shaping mechanism, and it offers time synchronization, which is the underpinning of different kind of traffic shaping. It offers a mechanism to provide redundancy to make its philosophy is to tolerant, make, and finally time critical by using different mechanisms. So in its toolbox, it has different mechanism like bandwidth reservation, as you can see in the slide. It offers different traffic shaping mechanism, and it offers time synchronization, which is the underpinning of different kind of traffic shaping. So it offers a mechanism to provide redundancy to make. Philosophy is to tolerant, make, and finally time critical by using different mechanisms. So in the toolbox, it has different mechanism like bandwidth reservation, as you can see in the slide. It offers different traffic shaping mechanism, and it offers time synchronization, which is the underpinning of different kind of traffic shaping. So it offers a mechanism to provide redundancy to make. Philosophy is to tolerate, make, and finally time critical by using different mechanisms. So in the toolbox, it has different mechanism like bandwidth reservation, as you can see in the slide. It offers different traffic shaping mechanism, and it offers time synchronization, which is the underpinning of different kind of traffic shaping. It offers a mechanism to provide redundancy to make. Philosophy is to tolerate, make, and finally time critical by using different mechanisms. So in the toolbox, it has different mechanism like bandwidth reservation, as you can see in the slide. It offers different traffic shaping mechanism, and it offers time synchronization, which is the underpinning of different kind of traffic shaping. It offers a mechanism to provide redundancy to make. Philosophy is to tolerate, make, and finally time critical by using different mechanisms. So in the toolbox, it has different mechanism like bandwidth reservation, as you can see in the slide. It offers different traffic shaping mechanism, and it offers time synchronization, which is the underpinning of different kind of traffic shaping. It offers a mechanism to provide redundancy to make. Philosophy is to tolerate, make, and finally time critical by using different mechanisms. So in the toolbox, it has different mechanism like bandwidth reservation, as you can see in the slide. It offers different traffic shaping mechanism, and it offers time synchronization, which is the underpinning of different kind of traffic shaping. It offers a mechanism to provide redundancy to make. Philosophy is to tolerate, make, and finally time critical by using different mechanisms. So in the toolbox, it has different mechanism like bandwidth reservation, as you can see in the slide. It offers different traffic shaping mechanism, and it offers time synchronization, which is the underpinning of different kind of traffic shaping. It offers a mechanism to provide redundancy to make. Philosophy is to tolerate, make, and finally time critical by using different mechanisms. So in the toolbox, it has different mechanism like bandwidth reservation, as you can see in the slide. It offers different traffic shaping mechanism, and it offers time synchronization, which is the underpinning of different kind of traffic shaping. So it offers a mechanism to provide redundancy to make. Philosophy is to tolerate, make, and finally time critical by using different mechanisms. So in the toolbox, it has different mechanism like bandwidth reservation, as you can see in the slide. It offers different traffic shaping mechanism, and it offers time synchronization, which is the underpinning of different kind of traffic shaping. So it offers a needs of the radio, there are classification of timing requirements for different types of scenarios. So the different classes allow like different amount of timing error in propagation. So timing error is, just to define the terminology, the timing error is the amount of error that is introduced in the synchronization signal all the way from the signal source to the consumer. So the table here in this slide describes, how the synchronization requirements are, driven by what that 5G use case is. So what that radio is doing. For example, for basic radio features like, TDD or, LTE coordination protocols, the allowable time error is 1.1 microsecond, which is very, relaxed, right? And this time error is between the grandmaster and the radio unit. And then, there are advanced scenarios where, for example, carrier aggregation, right? In this type of cases, the RUs can serve multiple RUs can be serving a single cell phone. So multiple radio units can be transmitting data to a single cell phone, and in those cases, the RUs need to be in absolute synchronization. So there are much lower time error levels here. So note that, I mean, important point to note here is that the above network here, it's the DU and the RU which performs the real time operations. So they need to be synchronized. But everything on the left here, the CU, for example, it does not do any real time radio functions, and therefore it does not have this, strict time synchronization requirement. And in a times very tighter time budget scenarios, the DU will typically be, will have a GPS input, right? So that the input of the time is closer to the time critical domain, and it will serve as a 1588 grandmaster for the RUs that it is serving. And every hop between the DU and the RU, that will need to be, 1588 or PTP boundary clock. It needs to understand 1588 for time distribution. And in some cases, there could also be, technologies like sync key used for, to improve the stability of the frequency base in this type of network. So what is important here is that the timing signals, they need to traverse the routers and the routers and all the time error actually gets accumulated, right, in each and every routers that are present in this path. So these routers will introduce some time errors, but they have to be classified, based on how much time error a particular node is, injecting. So every manufacturer will classify their products saying, okay, this is a device that injects this amount of error, and the operators, when they're implementing their network, they will pick and choose the devices based on this specification. So for example, a class C router will need to comply with error introduction of maximum of 10 nanosecond, as you can see in the table here at the right side corner. So, again, I mean, like I was also saying in one of the previous slides, frame preemption is a very new technology, as is time synchronization, and these technologies, they are coming very new in the switching hardware. And while adopting these technologies, the network designers, they need to think of all the, all the different kind of, components that are working properly. So that starting from adherence to the quality of service priorities, or the fragmentation, or the reassembly function at the switch. And finally, if the frame preemption is able to ensure that the end-to-end bounded latency is met. So preempting a non-time critical traffic can result in a lot of, erroneous conditions. For example, it can result in erroneous fragment generation, which can disturb the flow in the network, and it can so some kind of improper implementation can cause consequences, such as, a switch can generate, erroneous fragment, like I was saying, and which can jeopardize the time criticality of the front haul network. Or, while preempting, the preempted frames can suffer from added overhead and insufficient, insufficient amount of checks while doing the reassembly. So if there are erroneous fragments and the receiving side does not do the proper checks before doing the reassembly, there could be, again, erroneous traffic generated in the network. So to validate this type of use cases, there are different techniques used. So the switches can be connected with, there are tools that does this validation. So Keysight, we at Keysight, we produce tools for network infrastructure validation, and one of the tools, it's called IX network, that is typically used for this type of scenarios. And the way we do the validations is, this is typically the front hall network that you see here in the picture. Then to validate, you can replace the DUs and the RUs with specific hardwares like the Ixia chassis here, as shown in the picture. And this hardware can generate and analyze traffic through this network, and these hardwares can actually connect to the network based on the network, the link speed of the network. A front haul could be using something in the range of 10 to 100 gig, whereas the backhaul network, you'd be actually using something like a 400 gig link there. So based on the link speed, these hardwares can connect here and test the network, or if somebody wants to test a particular device in this network, so they can just connect the hardware directly to one of the switches or one of the routers in these networks, right? So it can connect to the front haul switch, as you can see in this picture. So one of the important tests to be performed specifically in context of preemption is it's to measure the latency of the express traffic in presence of preemption. Okay, so and this can be performed by using the IX network test ports to generate both express traffic and preemptible traffic from one side getting into the switch, and then receiving test port on the other side can check whether the proper fragmentation was done by the switch, and also measure the express traffic latency. I know these tests are performed in several steps here, but again, I'm not getting into the steps of the test here, but just wanted to give an idea about what kind of tests are important in this type of scenarios, right? The switch vendors also need to validate the reassembly function, and for that a typical test topology will look like what you can see in the slide. And this can be done by, again, using a tool like IX network that can generate preempted fragments from one side, and it can measure the integrity of the reassembled frames of the device on the other side at the receiving port. So we have talked about the different characteristics of the latency requirements in the front haul network. However, that was our main topic today in the presentation. However, I think before I kind of conclude, I would like to mention that this is just one piece of the RAN transport. So there are 6 technology pillars, I would say, that enables this flexible and disaggregated RAN architecture. The front haul is designed to carry the radio data encapsulated in Ethernet, as we said, and these, we discussed about its adherence to time synchronization. We discussed about its being able to provide certain bounded latency, but then there are the other things like the virtualization. For example, the network, the whole front haul, the mid haul network and the backhaul network, the DUs and the CUs, the elements that we have seen in the pictures in my previous slides, they could actually be residing inside a data center, and the connectivity between them could actually be designed inside a data center. So which makes the virtualization plane very, very important. Virtual RAN is a very popular theme. And then we have the segment routing based control plane, which is again very important because of the network slicing type of architecture being provided here. The front haul needs to support segment routing to be able to provide the network slicing to the higher layers. And finally, I would say that the security of this type of transport is extremely important. Again, the reason goes back to my first slide, where in case of an architecture where the base station was connecting to the radio using a dedicated fiber at the cell site, the chances of intrusion was much less. But in this case, we are talking about using a public network, the front haul network, to transmit these radio signals, and the chances of intrusion here is much higher. The security risks are much higher. The operators right now, they are considering different encryption techniques. Of course, MACsec is one of the very popular techniques that's getting considered, but there is always a question about the overhead that encryption brings in. So again, it's a choice between how much overhead, how much latency, what level of encryption you want. So a lot of questions to be answered here. So we at Keysight, just a little bit of glimpse on what we do at Keysight, right? So we at Keysight, we are providing test tools and test validation methodologies, starting from the R&D cycle to the QA cycle, and finally going towards the deployment for these devices. So we have the, like I talked about, the IX network tool, which is typically used for network infrastructure test, and then there are other, our partners, they use for conformance testing for protocol, like segment routing. If somebody is implementing segment routing, they would typically use like an IX Anvil protocol conformance test to validate that the protocols are conforming to the standards. There are tailor-made hardwares like the Novus here that supports TSN capabilities on different link speeds, and then there are softwares like CloudPake that supports NFV infrastructure test, the testing the infrastructure that hosts all this this full network, the RAN network that we talked about. So yeah, that kind of brings me towards the end of my presentation. I think I will end here. I think I've talked about a lot of technologies in a short time. Sorry if that was like too much of content, but 5G such a vast topic that I try to keep it as simple as possible, but then it's a vast topic. I had to use certain terminologies to complete this lecture. So open for questions.
Thank you, sir. Thank you for this interesting session on the burning topic of today's tech world, 5G. Differentiating between 4G and 5G infrastructure, and like what are the requirements for coming up with 5G and the 5G RAN infrastructure. So now I'd like to request the attendees of this session to use the Q&A feature, which must be present on your screen, to ask questions if you have any. So would be very open to any kind of questions you have. We'll be waiting for a minute or so to see if we get any questions.
Looks like a very silent audience today. No questions.
True, sir. One question has come up saying, how soon can we see the launch of 5G in India?
That's actually is not a, I would say it's not really a, technology question. It's more of a business decision of the operators in India. But what I would like to say is that, there are operators who are already working on it. The top operators in India, I can share only that much, and we know because we they use our testing services, but we are also under NDA not to share much about their roadmaps. But what I can say is there is already very active work going on in India, so we will see it soon.
Sir, the next question has come up saying, what is the impact of 5G on edge devices over 4G?
Okay, so here I would assume, so there could be two types of edge devices. One is what we call the user equipment, like the mobile phones and this kind of things, right? And this is also, this is extremely important because the 5G radio is a totally different standard from the 4G radio. It's called the 5G NR. So the equipment that needs to connect to a 5G enabled service will have to support the 5G NR stack. So it will have to have those new stacks enabled. And if we are talking about the efficiency of the equipment that are connected, for example, in an industrial automation case, there are cases where a complete factory can get automated using a 5G connectivity. Now we already have industrial automation where there are time critical robots performing time critical operations on assembly lines and etc. However, they were connected using wireline infrastructure like Ethernet. But with 5G, what we can achieve is, if it can provide the similar kind of latency guarantee, which it's supposed to do for URLLC, then we can also enable the moving parts in the factory, right? For example, a moving robot, which is impossible to connect using a physical wire. So they can also get connected over this 5G networks and then provide the similar kind of operations. And that's actually it's actually happening. It's not a theory anymore. It's happening in some part of the world.
Thank you, sir. Now, one more question is there, which is not very technological, but still I'd let you have it. How will 5G affect the environment? Like, it's more of an environmental concern. Like,
Yeah, and it's also a little I would say a little there is a political angle to answering this question, because there are different schools of thoughts on the 5G radio impacting the environment. But what I would say is that I don't at least I'm not in this domain, so I will not consider myself an expert on the environmental impacts. But from my perspective, I have not seen I have not seen any, at least scientific base of which says that the millimeter waves that are getting used will disturb disturb the environment or things like that. But again, that's a comment coming from a pure technology person, not an environmental expert.
Okay, so one more last question probably. Could you talk about the limitations 5G offers?
Well, I don't think, I mean,